Now wave front. A spherical wave front source to point source. Source point source. A spherical wave front source point source. Cylindrical wave front source is linear source. Plane wave front source point linear source at very large distance. Intensity of wave due to point source I is inversely proportional r square. Y in bracket r dash t is equal to a upon r sin in bracket omega t minus k vector dot r vector. Due to cylinder source I is inversely proportional 1 upon r. Y in bracket r dash t is equal to a under root r sin omega t minus k vector dot r vector. Due to plane source I is equal to constant. Y in bracket r dash t is equal to a sin omega t minus k vector dot r vector. Interference of waves y1 is equal to a1 sin omega t minus kx, y2 is equal to a2 sin omega t minus kx plus phi naught, y is equal to y1 plus y2 is equal to a sin in bracket omega t minus kx plus phi in vector a1 a2 phi naught phi, where a is equal to under root a1 square plus a2 square plus 2 a1 a2 cos phi naught, tan phi is equal to a2 sin phi naught upon a1 plus a2 cos phi naught. I directly proportional a square. I is equal to I1 plus I2 plus 2 under root I1 I2 cos phi naught. For constructive interference, maximum intensity phi naught is equal to 2n pi or path difference n lambda, where n is equal to 0, 1, 2, 3. I max is equal to under root in bracket under root I1 plus under root I2 whole square. For destructive interference, minimum intensity phi naught is equal to in bracket 2n plus 1 pi or path difference is equal to in bracket 2n plus 1 lambda upon 2, where n is equal to 0, 1, 2, 3. Minimum is equal to under root in bracket under root I1 minus I2 whole square. Degree of hearing is equal to I maximum minus I minimum upon I maximum plus I maximum into 100. Reflections and refractions of waves transmissions. Y1 is equal to a sin omega t minus k1x transmitted wave medium. Reflected wave Li is equal to Lr. The frequency of the wave remains unchanged. Amplitude of reflected wave AR is equal to in bracket V2 minus V1 upon V1 plus V2 AI. If V2 is greater than V1, that is medium 2 is rarer. AR is greater than 0, no phase change in reflected wave. AR is smaller than 0. AR is smaller than 0, there is a phase change of pi in reflected wave. As as a as AT is always positive, whatever be V1 V2, the phase of transmitted wave always remain unchanged. In case of reflections from a denser medium or rigid support or fixed end, there is inversion of reflected wave, that is, phase difference of pi between reflected and incident wave. The transmitted wave is never inverted. Rarer, denser. Yi is equal to ai sin in bracket omega t minus k1x. Yr is equal to ar sin in bracket omega t minus k2x. Yr is equal to minus ar sin in bracket omega t plus k1x. Denser yi is equal to ai sin in bracket omega t minus k1x. Yr is equal to ar sin in bracket omega t plus k1x. Denser yr is equal to ar sin omega t minus k2x. Rarer yt is equal to at sin in bracket omega t minus k2x. Bits. When two sound waves of nearly equal but not exactly equal frequencies travel in same directions at a given point due to their superpositions, intensity alternatively increases and decreases periodically. This periodic waxing and waning of sound at given positions is called bits. Bit frequency. Difference of frequencies of two interfering waves. Bit frequency is equal to f1 minus f2 stationary waves or standing waves. When two waves of same frequency and amplitude travel in opposite directions at same speed, their superpositions gives rise to a new type of wave called stationary waves or standing waves. Formations of a standing wave is possible only in bounded medium. Let two waves are y1 is equal to a sin in bracket omega t minus kx, y2 is equal to a sin in bracket omega t plus kx. By principle of superpositions, y is equal to y1 plus y2 is equal to 2a cos k into sin omega t. Equations of a stationary wave. As these equations satisfies the wave equations, del square y upon del x square is equal to 1 del square y upon b square del t square. It represents a wave. Its amplitude is not constant but varies periodically with position. Nodes amplitude is maximum cos kx is equal to 0. X is equal to lambda upon 4, 3 lambda upon 4, 5 lambda upon 4. Antinodes amplitude is maximum cos kx is equal to 1, x is equal to 0, lambda upon 2, lambda 3 lambda upon 2. The nodes divide the medium into segments, loops. All the particles in a segment vibrate in same phase. but in opposite phase with particles in the adjacent segment. As nodes are the permanently at rest, so no energy can be transmitted across them. That is, energy of one region's segment is confined in that regions. Transverse stationary waves in a stretch string, fixed at both ends, fixed end node and free end antinode. L is equal to lambda upon 2, fundamental or first harmonic or zero overtone. Lambda is equal to V upon 2L. L is equal to lambda. Second harmonic first overtone. F is equal to 2V upon 2L. L is equal to 3 lambda upon 2. Third harmonic second overtone. F is equal to 3V upon 2L. Nth harmonic in bracket n1 n minus 1 nth overtone. FL is equal to nv upon 2L. nv fixed at one end, fixed at one ends. L is equal to lambda upon 4. Fundamental. F is equal to V upon 4L. L is equal to 3 lambda upon 4. Third harmonic first overtone. F is equal to 3V upon 4L. L is equal to 5 lambda upon 4. Fifth harmonic second overtone. F is equal to 5V upon 4L in bracket 2n plus 1 th harmonic nth overtone. F is equal to in bracket 2n plus 1 V upon 4L. Sonometer fixed. Plucking friend. P number of loop. Fn is equal to P upon 2L in under root T upon mu. Sound wave. Velocity of sound in a medium of elasticity E and density rho is solid Young modulus V is equal to under root Y upon rho. Fluid bulk modulus V is equal to under root beta upon rho. Solid Young modulus V is equal to under root Y upon rho. Fluid bulk modulus V is equal to under root beta upon rho. Newton's formula. Sound propagation is isothermal. B is equal to P and V is equal to under root P upon rho. Laplace corrections. Sound propagation is adiabatic. Beta is equal to Y into P. V is equal to under root Y P upon rho. Some important point. With rise in temperature, velocity of sound in a gas increases as V is equal to under root Y RT upon m omega. With rise in humidity, velocity of sound increase due to presence of water in air. Pressure has no effect on velocity of sound in gas as long as temperature remains constant.